For the introduction. Thank you for the organization, for the honor of the invitation. It is a great pleasure to be in Denmark. So my name is Jacques Kools. I come from Belgium, but I lived in California, and so I'm a climate refugee. After that, I have to live in the south of France. So Encapsulix is based in the south of France. It's a company that I founded about 15 years ago. It's like Asterix, Obelix, and Encapsulix. We have the magic potion that makes invincible, meaning ALD coded barriers. So, let's see if it works. It does not. So the way I structured the talk is that, first of all, I will talk about philosophy. So I will talk about what is the quote-unquote universal problem of encapsulation, because everybody has corrosion problems and nobody is proud of it, okay? I have still come to see the first company that has to make a press announcement, major reliability problem in our products, okay? So we'll talk a little bit about performance, that if we want to mitigate, to stop is a big word, but to mitigate these undesired chemical reactions, or what performance do we want with the barrier? Why ALD? Why we want to use ALD and not something else? And the answer to that should not be, we happen to have an ALD machine and we want to put it to good use. And then I will talk a little bit about the work we've done at Encapsulix, something about equipment architecture and design, some material and process development, how that translates to device performance to the extent that I can talk about it, and say something about equipment architecture and industrial aspects. Okay, so as I said, when we talk about encapsulation, what do we talk about? You have devices, and devices is something to be taken in a very large sense. Products, they're fabricated, and during their lifetime, they will be exposed to chemical reactions with environmental products. And that could be as diverse as, in electronics, for example, the major thing is OLEDs. Organic light emitting devices are very sensitive for two reasons. Number one, you have these organic semiconductors, and if the molecule absorbs one water molecule, its band structure changes and it is no longer a semiconductor. And second, if you have a display, let's say you have an OLED TV and you have 2 square millimeters that is not working, you can throw it in the garbage. If you have a photovoltaics panel and there is 0.2% that doesn't work, you could live with that. You just have a little bit less power. So OLED is a big thing. We're working with 5 different makers of OLED displays in Asia, Europe, and North America. Augmented reality for professional applications is very well. Like, for example, the F-35 airplane does not have a dashboard. The controls are all through little augmented reality in the helmet, where the information is projected on the eye of the pilot. Flexible phones. Then LED micro displays is very similar, where you have an LED that creates white light and quantum dots that transform it into colored lights. Energy, there has been already talk about batteries and supercapacitors, so I'm not going to go too much into that. Perovskite PV, photovoltaics is, of course, it's very similar molecules. But as I said, a display is, through its nature, much more sensitive for damage than a photovoltaics panel. And of course, the cost price is not the same, right? Like this kind of, the display that goes into an F-35 fighter is per square meter much higher cost than your photovoltaics panel that you put on your roof. And the third one class is medical devices, where we've talked already before, it is implantable devices, so that devices that go into the body. And that there's really a big revolution there. The famous man from South Africa who works on electric cars and reducible reusable rockets. He has started to venture into that as well. And what you have in all different cases is that you have, as I said, you have chemical reactions with the environment. And if you can mitigate these reactions, you can have a longer lifetime of the device, less degradation. So that means from the environmental point, it's better because you can have less resources, less waste, less manufacturing, and so forth. Also, like for example, in the case of photovoltaics, if you can depreciation of your photovoltaics panels over 15 years instead of over 10 years, that means the price per kilowatt hour goes down. And finally, you know, if your patient has to be opened for service of the device every year or every 5 years in terms of patient well-being, that's also highly desirable. So, which brings us to what are the barrier requirements in terms of performance? What do we want? First thing, very important, we want no pinholes, okay? And we'll come back later to that, to let's say, discuss about that subject a little bit more scientifically. What do we mean? And what we see in practice is that a lot of barriers, they are really determined by the defects. It's not so much the intrinsic material properties of the material, it's the defects that determine everything. Second, it has to be adapted to the chemistry we're working with. And there's a variety of chemistries that are relevant, and these are really depending on the application. So as we talked, the organic semiconductors, the quantum dots that are used in OLED, perovskite, and so forth, they are very sensitive to just atmospheric water vapor and oxygen. You can have corrosive gases. And there's, for example, this is a very interesting example. You know, when they make watches, high-end watches, so I'm talking about watches that are like up to €1 million piece. When they do the leather of the watch band, they use chemicals for this. And I've heard that there is outgassing over time of sulfur-containing components from the leather that attacks the metal of the watch. And it is not my personal experience, unfortunately. But I understand that if you buy a €500,000 watch and black spots appear after a year, you don't appreciate too much, okay? And you have to pick up your phone and start yelling at somebody. That's part of the process. So salt water is something that you see actually quite often in marine applications. Also in automotive, you know, when they put salt on the roads, all automotive applications have to resist to. Bodily fluids, I'm a physicist, you know, all the subtleties of chemistry or biology escape me. Essentially, what the bodily fluids is salt water, okay? Blood, sweat, and tears is essentially water with salt in it, and then a little bit of other ions and some cells and so forth. But in terms of corrosion, if you have something that works against salt water, it usually works for bodily fluids. And there is something, this is very well established. For example, there is something called PBS, phosphate buffered saline solution, which is essentially, as I said, salt water with some KCl and some other salts that emulates bodily fluids. Or you have, like, in the textile industry, this is very well known, you have like artificial sweat. You can make a certain solution that emulates transpiration, because of course in the textile industry they want to have paints that resist to transpiration. So that's the, as I said, depending on application, you will need to have different chemistry, and that means that we need different materials for different applications. And then there's a secondary functionality, okay? Optical properties, appearance are important. If you have an optical device, you need to have transparency. You may want to have antibacterial properties, which is really cool. That something is like auto-disinfectant. Something which I think is also very cool is to have a barrier that is a multi-layer that includes a transparent conductive oxide. So you can have something which is also a Faraday cage. So it prevents electromagnetic signals from leaking outside of the device. And then, of course, there is the process temperature. Like, for example, the organic semiconductors, they should not go over 100 degrees. And there is the cost. At the end of the day, that's important. And that depends also on the application. On a $500,000 watch, €500,000 watch, you can be a little bit more flexible in terms of cost than on a €100 photovoltaics panel. Okay. So I will go quickly. We've done some modeling on the effect of defects for the different on what a pinhole really looks like. And we've done, this is something where we've done modeling and we've done measurements on something which is called the double water vapor transmission rate, which is a way of quantifying a barrier as a function of the defects. And so what you see is that if you want to have typically what people are looking, what they call an ultra barrier, so 0.1 milligram per square meter per day, which is actually all it needs better barrier than that. It corresponds to a single 0.6 micron defect per square millimeter. Okay, so in terms of defectivity, you really that's a key point. You really need very low defectivity, and that is why we use ALD. That phrase there is the single reason why we use ALD, because it allows us to have much lower defectivity than other alternative techniques. So we at Encapsulix, we developed a architecture which we call parallel precursor wave. We used to call it tsunami until what happened in Japan, and then we stopped using that term. And that allows to do temporal ALD, not spatial, but much faster than traditionally. And we do that by our reactor is essentially a waveguide, where we flow composition waves of precursors through it. And that allows us to enhance the throughput by a factor of 30 to 100. For example, this is the classical example, TMA plus water vapor at 80 degrees C. You see this famous paper from Stephen George, Jeff Elam, where they have at 80 degrees C purge times of 5 and 20 seconds. And these are GPC and optical index data as a function of purge time. And you see that for TMA, we can work at 150 milliseconds, okay? 150 milliseconds, 500 milliseconds for water vapor. So we can do really 30 to 40 times faster. And we can do deposition, like, for example, and if we can do PALD also, we can do dep rates, let's say here 60 junction per minute for silicon oxide at 65 degrees. Aluminum oxide PALD, we can do 100 junction per minute. So it really is orders of magnitude. It's not just that we are faster than the other methods, we still have time to drink a cup of coffee before they arrive. Okay, and it's a good barrier. So people like Pete Garcia, when he was at DuPont Research, or Stefan Cross at CANS have measured, and it's a good barrier. You can make devices with it. Other materials, we've been working a lot on titanium oxide. And titanium oxide works very good against salt water. So these are measurements of the thickness into what is called the salt spray test. We talked about salt water a lot. So this essentially, you do a vapor of salt water, continuously jet of salt water, okay? And this is over 18 days, which is a really long time. And you see that the thickness really doesn't change. The titanium oxide comes out as a mirror. So titanium oxide is very good for salt water. Okay, so that's at the materials level. Now, if we go to devices, so it was used since 2014. So for 10 years now, has been used for OLED applications. Next time you're in Paris, if you go to Châtelet-Les Halles, which is like a big train station, you see these light sculptures with OLEDs. These are made with our equipment. These are OLED small silicon transistors devices. And this is from Cieletti, where you see an IV curve of an OLED devices as it was made and 2 years later. And as you can see, there is nothing to see. 2 years, there is no degradation in the IV curve of the device. This is photovoltaics, same thing, where you see the damp heat results of photovoltaics, the output voltage as a function of time. For those in the back who can't see it, this is 4,000 hours of damp heat. So that we had to stop the experiment because they needed the installation, but that's the equivalent of 20 years. So you double the lifetime from 10 years to 20 years. That even a politician can understand. So how does it translate to equipment? We use, we've got a number of different things. This is a 200 millimeter version where we use a very modular system. So for example, our sources, these are water sources. These are different metal precursor sources, ozone generator. So this is a typical tool, 4 metals, 3 gas, water, ozone. It has plasma also. And this can be coupled to a, like a cluster, you see. This is a larger tool for large glass panels, 500 by 400. This has been used on large substrates, 370 by 470 millimeters. At ALD cycle times less than 1 second for 85 degrees, where it was really thousands of depositions a year. And you see here some stability over a month. And you see it's like essentially plus or minus 1%. Variation over 1 month of operation. Okay, and this is where I would like to go to the discussion, is that this is one of our customers made an OLED with our logo. And this is the OLED in 2015. This is the same OLED when I cleaned up my office in 2023. So you know what frequency I clean up my office. And you see that it still worked nicely and no black spots. Thank you for your attention.
Thank you very much, Jacques, for this overview.
Yeah. What were the thicknesses of when you were doing the encapsulation?
Well, the thickness, it depends, but like, for example, this is 500 cycles ALD. 500 cycles aluminum oxide, so it's like 43 nanometers.
The back?
You are talking about quality after the measurement.
I wasn't there, so I can't tell you. But they didn't tell us exactly what they did. But I understand that it has been, you know.